Molecular mechanisms for water flow through a new nanopore geometry for desalination techniques to convert seawater to drinking water have been identified by Indian Institute of Technology, IIT Madras researchers. Researchers from Swinburne University of Technology, Australia, and the Delft University of Technology, the Netherlands, collaborated on a study that aims to improve the design of carbon nanotube-based reverse osmosis systems. They drew inspiration from nature, specifically biological systems, for the development of efficient desalination membranes. Project funding for this study came from DST, India's Department of Science and Technology, DST, responsible for developing India's water technology, WTI. More than 100 million people will be impacted by groundwater depletion in 21 major Indian cities, including Chennai and New Delhi, by 2030, according to a report from the National Institute of Industrial and Strategic Research, Niti Aayog. For domestic and industrial use, scientists worldwide are investigating methods for repurposing saltwater from seas and oceans. Desalinating seawater has been suggested to solve India's water shortages because the country has a coastline of around 7,000 kilometers. Many desalination technologies are available today, but their high energy consumption limits their widespread adoption. It was led at IIT Madras by Sarit P. Sathiyan, Department of Applied Mechanics. His team has been developing better desalination membranes using nanoscale water transport through carbon nanotubes and graphene nanopores. Sridhar Kumar Kannam from Swinburne University of Technology, Australia, Vishnu Prasad Kurupat, and Remco Hartkamp from the Delft University of Technology, the Netherlands, were part of the team. Published in Desalination, the peer-reviewed journal, are the findings of this study. In the long run, the following are the potential practical applications of this research. The method of separating the solvent from the solute. Membranes that can be altered and/or selectively transported, ion selectivity and drug delivery. Analyzing and comparing the nanopore geometries of various materials inspired by biological processes. For the development of artificial organs, water dynamics inside biological nanopores are being studied. Because of the hydrodynamic resistance at their entrance, graphitic carbon materials tube-like structures have lower permeation rates than conventional raw membranes, despite studies showing that they can permeate more water. Biological systems for making efficient desalination membranes were a source of inspiration for the research team to solve this problem. According to Sathiyan, our study has opened up the inside view of water and ion permeation through nanoporous synthesis. They shed light on the mechanisms that allow water to pass through hourglass-shaped nanopores more easily. Because of this, it is possible to use a different system of nanopores to achieve a higher desalination efficiency. First and foremost, the membrane's ability to reject ions during desalination is an important consideration. According to our research, the synthesis has a major impact on ion rejection. A nanopore geometry with high permeation capacity and low ion rejection could thus be conceived.